In our previous video, we were talking about the mechanism of HBr addition to an alkene. And we noted that there were two pieces to this, the bonds made and bonds broken, and then the order of the events. And we listed the bonds broken and formed. And what we wanted to do, hey, let's figure out what order they were formed in. Okay, and we're going to do that, but we're going to introduce a couple more things along the way. Hey, get out of here. Okay, first we're going to introduce this arrow notation. Okay, this is something that is, I'm going to go with the word peculiar, or you could say unique, to organic chemists, but it is definitely something that we use. This is an arrow, a little curved arrow. We use them a lot. We use them to illustrate mechanisms. So you might have a question that says, show the mechanism using curved arrows. The beginning of the arrow, which is where the A is the start, and then the end of the arrow, which is the pointy part, is the end. And the arrow symbolizes the flow of two electrons. Here, in this case, two electrons from A are flowing to B. And it doesn't say here, but A and B, the product of this action is that A is going to form a bond to B. The originator of the arrow, that's A, is going to be called a nucleophile. And that is an electron-rich thing because it's going to originate these two electrons. A nice, easy nucleophile that we can keep in our head is hydroxide, HO-. It's a fairly familiar compound, and you have some idea of what it does, and that's a fairly typical nucleophile. And hydroxide, you say, is also a base, and nucleophiles are often bases, and bases are often nucleophiles. They're different, but they're similar. Receiver of the arrow. The receiver of the arrow is called an electrophile, and that's electron poor. And one electron poor species that we can think of is H+, but we'll see other electrophiles. It's typically harder for students to identify electrophiles than it is to identify nucleophiles, but we will point them both out. Okay, now that we have that basis, we can look at pretty pictures like this. So imagine the words weren't there. That diagram to the right has real meaning to an organic chemist. Okay, so the arrow is two electrons, and they're where they're going. Let's read this. Starting from the beginning of the set of two arrows, two electrons start from the C double bond C, and then they attach to the H of the HBr. That's what that arrow means. The carbon, one carbon gets the H. It looks like here it's the right carbon gets the H. So the left carbon gets a positive charge. And why is that? Well, there were two electrons in a bond. Those two electrons left the bond to form a bond to the CH. Well, that leaves a hole or a plus charge on the other carbon. Now, how about the HBr? Well, that used to be a two-electron bond, but one of the C's grabbed that bond. So where do the other two electrons go? They go onto the bromine atom, and some of the bromine atom has a minus charge. And we'll see that the charges are conserved. The left side has no charge on either species, and the right side has a plus and a minus. Br gets the negative charge. The alkene, which is the originator of the arrows, is the nucleophile. Doesn't look like hydroxide at all. And HBr is the electrophile. In this case, it looks like sort of our H+, which is our prototype. How about step 2? See, this is step 1. We're not done. This is step 2. In step 2, I've got a bromide, and the Br- forms a bond to that other carbon. So the bromine uses two electrons to form a bond to the C+. And in that first drawing, you see how I drew that ridiculously long carbon-bromine bond. And I did that to show you that nothing else changes. The only thing that's going to happen is I'm going to form a line there. And then in that equal sign shows you that I'm just basically redrawing it in a neater fashion. The Br- is the nucleophile. It has a minus charge. Lots of nucleophiles have minus charges. The carbon plus is the electrophile. It's the whole 2-butyl cation. That whole thing is the electrophile, but the electrophilic center is the C+. Okay, let's summarize this. It's a two-step process. Look what happens in the first step. Two of the bonds break and one bond forms all in one step. And in the second step, one bond forms. So earlier when we looked at the possibilities, we said that 4 things could happen. You probably wouldn't have guessed that 3 of them happen in the first step and that 1 happens in the second step. Okay? We also noticed that there's a carbocation that's an intermediate. What's an intermediate? An intermediate is something that forms along the way, but it's not part of the products. And we see that it's not part of the products. That's going to introduce another concept, and this is our last concept for this video. And this is in an earlier chapter in the book, not in the alkene chapter, but it comes up here. So there are transition states and intermediates. Transition states are things that we pass through. Intermediates are states that we visit. Notice we can live somewhere, that means we stay there a long time. We can visit it, which means we stay there for a little while, or we can pass through. So if I throw a baseball, which you don't want to see, but if I were to throw a baseball and it goes through its maximum height, it has some kind of arc to it, that's a transition state, right? Because it's not like it ever stops at that highest point, it just goes through it. But an intermediate is someplace that I visit. I'm going to try to do this demo, but it's not going to work. See, I'm going to try to balance this pen on my finger like that. I'm really not good at it at all. It says stays for a few seconds, and then it stays for a fraction of a second. So an intermediate is a thing. It actually exists for a little bit of time, and then eventually it falls over into something else. Transition state is not. And we can put this in this energy diagram, and I think this is our last little bit. This is a reaction coordinate diagram, and it's really nice for showing a mechanism. So this is the mechanism for HBr addition. Now, that drawing looks a little ugly. Imagine that those lines were actually smooth, that it went like lumpy, lumpy, lump. My drawing program and I are not on good speaking terms right now, and it said, I will show you. Anyway, the y-axis is energy, so I can see points that are high in energy. Bear in mind that low in energy is where things want to go. Okay, things tend towards low energy. If you're asleep on the couch, that's low energy. That is where chemicals like to go. They like to be asleep. If they're a high energy, that means they're highly reactive. And what do highly reactive things do? They react to become low energy things, and then they don't react. So let's look at some points here. The triangle is a starting material. The square is the product. So the x-axis shows the reaction progress. You could imagine it's like an axis that says time, but it's not in seconds and minutes. It's in the reaction going through the steps of the reaction. If the energy of the triangle is higher than the energy of the square, which is fairly typical, then the reaction is exothermic, which means it gives off heat. The opposite would be endothermic reaction. Okay, what's that circle there? You can see that circle is a sort of a low point. And if you look near the circle, it's the lowest point around. But if you go a little further out, you realize that the triangle and the square are lower still. That's what an intermediate is. It's sort of trapped in a well where locally, nearby, okay, it's the lowest energy. But globally, looking at the whole thing, it's higher. So an intermediate is typically, almost always, higher than the triangle, higher than the square, but it's lower than the highest points. Those highest points, those lumps that go up, are transition states. Now notice those transition states don't look like good resting spots at all, right? If you were there, you just sort of fall off. So transition state is, again, something I pass through. It doesn't have an actual lifetime. And they're the highest points on a surface. Sometimes there could be one transition state or two transition states. And they're also responsible for the reaction barrier. In order to get from the triangle to the square, I have to overcome the barrier, which is those high points. I need to put energy in to break all those bonds before I can make those bonds. Of the two arrows, the higher of the two arrows is what's called the rate determining step, or the slow step. This is the maximum amount of energy, if you want to think of energy as money, the maximum amount of money that I need to spend in order to get my reaction to go. Okay? It's also called the slow step, because the other step I have to spend less money, so it happens faster. And the overall rate of the reaction, how fast the reaction goes, depends on this step, the rate determining step, but not steps that follow it over here. So, yeah, we'll just go with that. Anyway, that's the end of our show. What we would like to do is see, we should be able to draw with arrows the mechanism of HBr addition to an alkene. And we should be able to see how it forms an intermediate and how that maps onto this diagram over here. Because I formed a carbocation intermediate, that first step over here is for the alkene is actually rate determining. There is another possibility, but that's not the one that we see. Anyway, we're going to wrap up that video with that.